Okay, hello. Uh, so we are now on open methods. So open methods are an alternative solution or another solution in finding the roots of a given function. The main difference, okay, so if we're going to compare it with the bracketing method, is that it only requires a single starting value of x or two starting values that do not necessarily bracket the root. So for bracketing method, so we need two initial values. So we're in it brackets the initial or the roots. So for us to find the root of the given function. And then in terms of the convergence, so when open methods converge, okay, so when open methods converge, they usually so much more quickly than the bracketing methods. Bracketing methods, the main advantage of bracketing methods is that it will surely converge. For open methods, there's a possibility of divergence. However, if it will converge, okay, so it will converge faster as compared to that of the bracketing method. So for open methods, there are actually four. So we have the simple fixed point iteration. We have Newton-Raphson method, the second method, and the modified second method. Simple fixed point iteration and Newton-Raphson method so uses a single initial value. So modified second method and the second method so uses 2 points. Or sorry, the second method uses 2 points and then the modified second uses 1 point. However, so for this discussion, so we will just limit our discussion with simple fixed point iteration and the Newton-Raphson method. So under the fixed point iteration, so which is an open method, so we predict the root by rearranging the function f of x is equals to 0 so that x is on the left side, it's on the left hand side of the equation. So if we are given a certain function of f of x, so we equate that function to 0, and then afterwards, so we transpose the x to the left hand side, and the remaining function so will serve at the right hand side of the equation. And then from there, so we do the iteration, so by just simply substituting, okay, so substituting the initial value for x using the g of x function. But then, so the transformation of the equation so can be done so through algebraic manipulation or just by adding x to both sides of the original equation. So x is equals to g of x, so provides a formula to predict a new value of x as a function of an old value of x. So usually we are given an initial value and then we just substitute it to x, and then from there, so we will get, okay, or we will be able to find the new value for x, and then afterwards, so we compute for the approximate error. If it is already below the specified stopping criterion, then we stop. But if it is still above, then we redo the process. So usually, so this would be a flow chart. Okay, so for simple fixed point iteration, okay, so recall, okay, so the process in creating a flow chart. So usually, so we have this oval type figure, so for the start of the program, and then so we have the input, okay, so we have the input entries, so that would be, the first one is we're going to define the f of x. Okay, so defining the f of x, so will let us determine or will give us an idea on what will be our equation. Okay, so defined f of x, and then afterwards, so we need, okay, so we need the initial value or that is the x sub 0. So x sub 0 is our initial value or our initial guess. And then the maximum error, so that would be the stopping criterion. Okay, so we need to get those values because that would tell us if we're still going to continue with the iteration or not. Okay, so if you're going to create a certain algorithm or a program for simple fixed point iteration, so this is how it goes. Okay, so the first one is we're going to set n is equals to 0. So that would serve our first iteration. Okay, so when n is equals to 0, and that one increments. Okay, so whenever there is a repetition on the iteration. And then so the rectangle part here, so that would be the process for the second process. So after setting n is equals to 0, so that is the one that we're going to get the x raised to n plus 1. Okay, so that is the next value for x. So the next value of x can be taken so by substituting the previous value of x, okay, so to the given function. Okay, so x of n plus 1 is equals to the given function. So now we have a new value for x. Okay, so for the new value of x, so we increment, okay, so from 0. So next would be the n plus 1. So that is that would correspond to the next iteration. And then, so once we increase, okay, so once we once we were able to find the new value for x, so there is a decision here. Okay, so the diamond figure here. So we're going to get the difference between the new minus the previous one. The x of n plus 1 is the new value, and then minus x of n, which is the previous value. So from there, so it's either we're going to get the this just the true error, or we could even find, or sorry, so this would just be the approximate error. But then if we want to find the percent relative error, so that would be okay. So as long as it is greater than the maximum error, okay, so greater than the maximum error, then the iteration continues. So we go back, okay, and then there would be a series of increment. So if it is already no, so that means it's already below, okay, so which is below the maximum error or the stopping criterion. So that is the time that we're going to print the root, okay, or that is the time, okay, so that we're going to show so what will be the root of the given function. Okay, so that is how the simple fixed point iteration. So for the Newton-Raphson, it's still the same. So the only difference is the formula. Okay, so that we're going to put an entry 2. Okay, so we have to recall this one on how to create simple fixed point or flowchart. Okay, so how to create flowchart. It might be useful. Okay, so later on. So let's have our first example. So first example is we're going to use simple fixed point iteration, so to locate the root of f of x equals to e raised to negative x minus x. So use the initial value of x of 0, and then 5 significant figures for the value iterated roots and 3 significant figures for approximate. Okay, in this case, we're not going to solve the true relative error anymore. So to save some time, so we're just going to focus with the approximate error. Okay, so our first step here, so it says that we need to set f of x to be equal to 0. So in here, so our f of x is equals to e raised to negative x minus x. So thus, e raised to negative x minus x, so will be equal to 0. Okay. Or we could make this one as just simply 0 is equals to e raised to negative x minus x. And afterwards, so it's either or I'm going to add x to the left hand side or to the right hand side of the equation. So doing that, so that would give us x is equals to e raised to negative x minus x plus x. Okay, so we add, so 0 plus x on the left hand side, and then e raised to negative x minus x plus x at the right hand side. So finally, so giving us the x to be equal to just simply e raised to negative x. So because this one would just be equal to 0. So now, so we have our equation. So x is equals to e raised to negative x. So in finding the root of for x, so we substitute our initial value. So this time, so this will be our formula. So that would become x I plus 1. Okay, so it's the next value is equals to e raised to negative x times I. Okay, so which is the previous value. So x of I plus 1 is the next value. So e raised to negative x of I is the previous value. So in this case, so we start with x. So it says here that our x of I is equals to 0. So from here, x is 0. And we don't have the approximate error. So for our first iteration, it would just be e raised to negative 0. So e raised to negative 0, that is just equal to e raised to 0, which is 1. And then, so we can write, okay, so for our approximate error, so which is the present, so 1 minus 0 over the present, so times 100%, so that would make it 100%. So by the way, it says that it should be 5 significant figures, so I'm going to follow that. 1, 2, 3, 4. Okay. And this one is 100%. So for the approximate error. So for our second iteration, so this time, okay, so our previous value is 1. So therefore, so for the second iteration, so this would be, so x of I plus 1 is equals to e raised to negative 1. And so our e raised to negative 1. So which is equal to 0.36788. 0.36788. So for our approximate error, so previous is 0.36788 minus 1 over 0.36788. So times 100%. .36788 minus 1 over 0.36788. So times 100. So that is too much. So 171 point. Okay, so 3 significant figures, 172. Okay, so 172%. So that is for the second iteration. So for our third iteration, so x sub I plus 1 will be equal to e raised to negative 0.36788. So shift e raised to negative 0.36788. So which make it 0.69220. And based on that one, so we can compute for the approximate error. So to be 0.69220, so minus 0.36788. So divide it with 0.69220. So times 100%. So giving us 0.69220 minus 0.36788 divided by 0.69220. So times 100. So we have 46.85. 46.9%. So that is 0.69220. 69220. We have 46.9%. And which is far below 0.2%. So we need to do the fourth iteration. So our x sub I plus 1, so this will be e raised to negative 0.69220. So shift e negative 0.69220. So which is 0.50047. 0.50047. So 0.50047 minus 0.69220 over 0.50047. So times 100%. So that is 0.50047 minus 0.69220 divided with 0.50047. So times 100. So we still have 38.3%. 0.547. 38.3%. Okay. So still far, 0.2. The process is simple, but the convergence is a bit slower. So x sub I plus 1 is equals to e raised to negative 0.50047. So that will be equal to, so shift e raised to negative 0.50047. So that makes it 0.60625. So our approximate error 0.0625 minus 0.50047 over 0.060625. So times 100%, 0.606625 minus 0.50047 over 60625. So times 100. So which is 17.4. 17.4%. 6625. 6625. 17.4%. Okay. So we proceed with 6 iteration. So x sub I plus 1 is equals to e raised to negative 0.6625. E raised to negative 0.6625. So 54539. So 54539. Our approximate error 0.54539. So minus 0.6625 over 0.54539. So multiply it with 100. 0.54539 minus 0.6625 over 0.54539. So times 100, that will become 11.16. Uh, 0.54539. What is it? 11.16 or just 11.2. Okay, so 7th iteration. So x sub I plus 1 is equals to e raised to negative 0.54539. Shift e negative, so negative 0.54539. So that makes it 0.57962. 57962. So our approximate error 57962 minus 0.54539 divided with 0.57962. So times 100, 0.57962 minus 0.54539, 54539, and then divide with 0.57962. So times 100, so that is 5.91%. 57962. And we have 5.91%. For our 8th iteration, so we have x sub I plus 1 would be equal to e raised to negative 0.57962. So which is negative 0.57962, 962, which is 0.56011. 0.56011. 0.56011 minus 0.57922 over 0.56011. So times 100%, 0.56011 56011 minus 0.57962 over 0.56011. So times 100, so we'll have 3.48. Five six zero one one 3.48. Okay, so 8 for 9th iteration. So e raised to negative 0.56011. Shift E negative 0.56011. So we have 0.5715. 0.7115. So 0.57115 minus 0.56011 over 0.57115. So times 100%, 0.57115 minus 0.56011 over 4.57115. So times 100. So 1.93. 0.57115. And for the 10th iteration, so x sub I plus 1 is equals to e raised to negative 0.57115. So shift E negative 0.57115. So it's 0.56488. 56488. Uh, 5711 56488. And 0.56488 minus 0.57115 over 0.56488. So it's still 1.12. 0.56488. Okay, so we proceed with 11th iteration. So x sub I plus 1 is e raised to negative 0.56488. 0.56488 should be negative 0.56488, 9.5. So that is 0.56843. 0.56843. 0.56843 minus 0.56488 over 0.56843. 0.56843 minus 0.56488 over 0.56843. So times 100. So we have 0.625. 56843. Point 625. So point 2. Okay, so that's too much. Okay, so we'll continue. We're already here. So exabyte plus 1, so would be e raised to negative 0.56843. Shift e negative 0.56843. 56843. So that is 0.5664 56641. 0.56641 minus 0.56843 over 0.56641. So times 100. 0.56641 minus 0.56843 over 0.56641. So times 100. So it's still 0.357. 0.56641 0.357. And then the 13th iteration. So exabyte plus 1 is equals to e raised to negative 0.56641. Shift e, so negative 0.56641, which is 0.56756. 56641 56756. So approximate error 0.56756 minus 0.56641 over 0.56756. So times 100. 0.56756. 56756 minus 0.56641 over 0.56756. 56756, 56756 times 100, which is 0.22%. So we need until 14th iteration. So exabyte plus 1 is equals to e raised to negative 0.56756. 56756. Negative 0.56756. So it is 0.56691. 0.56691 minus 0.56756 over 0.56691. So times 100%. And that should be 0.56691 minus 0.56756 over 0.56691. And then times 100. And that gives us a 0.115%. 0.56756. So 11, 12. Okay, so the solution is there. The table is just not complete. Okay, so it should be until the 14th iteration. And that is simple fixed point iteration. The process is very simple. It's not that complex. So there's no complex mathematical formula that we're going to use. But the convergence is not that fast. Okay, or it's slower actually. So an alternative method, so for the simple fixed point iteration, will be the Newton-Raphson method. So under the Newton-Raphson method, so it uses this formula. So it uses the tangent line. Okay, so in predicting future values, so that is why. So we have this. So we have this formula that is the x sub I plus 1 is equal to x sub I, so minus f of x sub I all over f prime of x sub I. So we need the function and then the derivative of the function, so for us to find the value of the x sub I plus 1. So from there, so we substitute. Okay, so from there we substitute. Okay, so we have the same example. So the same requirement. So we're just going to solve it using Newton-Raphson method. So let's try to solve it. So I'm going to copy this one. Oh. So we have another table, so which is blank. So I'm just going to use that one. Okay, so for the Newton-Raphson method, so our general formula so will be x sub I plus 1 is equals to x sub I, then minus f of x sub I all over f prime of x sub I. Okay, so suggested by this given formula. So in this case, so we are given the function. Our f of x is equal to e raised to negative x minus x. So to find for f prime of x sub I, so we need to find what is f prime of x. So the derivative of e raised to negative x is e raised to negative x. And then derivative of negative x is negative 1. So that would give us negative e raised to negative x. And then derivative of negative x is negative 1. So f prime of x will be negative e raised to negative x minus 1. So that's our general formula this time. So would be x sub I plus 1. So will be equal to x sub I. Then minus. So we change x to x sub I. So that is our f of x. So which is e raised to negative x sub I minus x sub I all over minus e raised to negative x sub I minus 1. So that is our formula. Okay, so in finding the next value. Okay. So that is why for our first iteration, so we just substitute. So I'm going to use the table. So our given function then will be alpha x, then minus shift e raised to negative alpha x, then minus alpha x over negative shift e negative alpha x minus 1. So I'll start with 0. Okay, so since our first iteration will be 0, so when x sub I is 0, so I'll start with 0. So let me see. Okay. Can I go back? And clear. Start of 0, end of 0, step of 0. Okay. So I can't do the 0, so we'll start with the table later on. So I'll just substitute first. So we have x sub I plus 1 is equals to x sub I 0, then minus e raised to negative 0, so minus 0 over negative e raised to 0 minus 1. So from here, so we have 0, so minus e raised to 0 is 1 minus 0, and e raised to 0 is 1 minus 1. So that makes it so for the initial value, okay, so when it is 0, so we have a 0. Okay, so for the okay, e raised to 0 is 0, and then so I'll have a negative there, so negative 1 minus 1, so that would give us a 0, so minus, that is 1, and negative 2, so which is 0.5. 1, 2, 3, 4. Okay, so for our first iteration, so when x sub I is 0, so for our first iteration, this would be 0.50000. And then, so obviously, so this will be 100%. Because 0.5 minus 0 over 0.5, so that is 100%. So I'll proceed with the second iteration. Okay. So for the second iteration, my x sub I this time, it's 0.50000, or just simply 0.5. Our x sub I plus 1 then, so will be equal to, did I clear that one? So I'm going to input it again. So alpha x minus, so shift E, negative alpha x, and then minus alpha x. Divide it with negative shift E, negative alpha x, and minus 1. I'll start with 0, and then the end will be 0.5, and the step size would be 0.5 as well. So giving me 0.56631. And then my approximate error, 0.56631 minus 0.5 over 0.56631, so times 100%. So I'll try this one for until fourth iteration. I don't want to lose my function in case I don't want to type it again. So I'll proceed with the third iteration, then I'll compute for the approximate error later on. For my x sub I then, so will be 0.56631. I'll start with 0. I'll end with 0.56631, 0.56631, and I'll end with 0.56631 as well. So giving me for my x sub I plus 1 to be 0.56714. 0.56714. And then for our fourth iteration, so our EA here will be 0.56714 minus 0.56631 over 0.56714. So for our fourth iteration, so x sub I is 0.56714, and our x sub I plus 1 will be, I want to clear that one, so 0, and then it will end to 0.56714, 56714. And as you can see here, so it's already the same. So most probably our approximate error here is already 0%. For our second iteration, 0.56631 minus 0.5, so divide it with 0.56631, so times 100%, so it's 11.7%. So for the other one, 0.56714 minus 0.56631 over 0.56714, so times 100, so that is 0.146%. So as you can see here, so it's only the third iteration, 0.5631. That's 11.7 from 100 to 11.7%. Then 0.56714, 0.146. And it's already below the stopping criterion of 0.2. So this one is 0.146%. And as you can see here, so the Newton-Raphson, okay, so is faster, very fast as compared to that of the simple fixed point iteration. So since this one uses the tangent line, so in predicting future values. Okay, so again, so as a recollection, open method, okay, so open method so converges faster as compared to bracketing methods. Okay, but the advantage of the bracketing methods is that it will surely converge. But for the open methods, although it is faster, there's a possibility of divergence. So meaning there's a possibility that it won't go, okay, so to the roots of the given function. But once it converges, okay, so it converges the fastest way possible. So these are actually the pitfalls of Newton-Raphson method. So as you can see on the given graph, so this would be the root. Okay, so this is the root of the graph. So usually, so since it uses the tangent line, so the line that touches only one point of the graph, so if the function is whose graph is like this one, so there's a possibility that during the first iteration, so we'll have this value for the x sub 1, and then so we form another point. Okay, so for the second iteration, and then we'll go to another second line. So the one that crosses the x, so would be the x sub the new value for x. And then afterwards, so we're going to have a new value, and then since the point of inflection here, okay, so it's within the x-axis, there's a possibility that we are diverging. Okay, so meaning we are going far from the roots. Okay, so instead of converging it closely to the root, so it goes further and further away from the root. So the same is true with this one. So if we have a sinusoid, so for the given function, so since it uses a tangent line, so there's a possibility that it will go to the other points of the line. An initial guess that is close to the one root can jump to allocations to several roots away. So that is possible as well in Newton-Raphson. There's also a possibility that it will, one of the problem is if the difference, okay, so if we got an f prime of x, so which is equals to 0, so that means that will be an undefined root. So if the slope will be 0, so similar to this, so let's say we arrive at this particular point, so the slope is 0, that means f prime of x is equal to 0, so then that will yield to an undefined value for the x. So those are the pitfalls, okay, of Newton-Raphson method. So the possibility that it will diverge. So there's a possibility that it will diverge. But if it will not diverge, so meaning it will converge, it is faster as compared to the bisection method. Okay, so for your assignment, so you answer this one and you submit it on your Canvas module. That will be all. Good day and God bless.